Okay, good morning. In the next talk, Erwin Erkinger, a software engineer and project manager, will tell us about the process by which the aerospace company develops and designs software safe and reliable. Please give a warm welcome to Erwin.
Thank you very much. I'm really astonished that so many people are interested in that topic. Further on, I have to clarify, this talk is about the software process. At least it's a teaser. It's not a detailed description because the process the aerospace industry is using is quite huge. No mysteries will be revealed, like why planes don't drop out of the sky. So you've been warned. If you're still interested, I have 3 parts of my talk. An introduction where I just want to try to give you an impression what reliable software could be and what it is for aerospace industry and how it's defined, or how it could be defined. Then the software process in itself, and at least a conclusion where I just think that it's quite good to have an idea of how this process could be used for the Linux community, or open source, or whatever. One thing which is very important for me is that Thomas Cleriel, long time ago, just stated that the greatest fault is to be conscious of none. And that's very important. Faults will be made, errors are inherent. For aerospace industry, it's quite clear, reliable software, there's no way around. But for commercial application, this is also an issue. If we are thinking back in 1990, where $1.9 billion are lost because of misplaced break in a small C program on the AT&T switches. Telephones went out and only the busy line would be held. Of course, the famous Ariane 5 accident in 1960, where a float was forced into an integer in a non-critical component. Or quite new, the Dell web shop just sold PCs for €5 instead of 588 because of a configuration failure. So I think reliable software is also an issue for non-critical applications. And if you have a look at a typical, let's call it web application, it's huge. It's really huge. 10K to 1 million lines of code, heavy reuse of multiple modules, and often the developers are unaware about the underneath architecture. Typical threads, you know more than me, so I just had it on my sheet. So the chance for a serious error is quite high, I would say. But what is reliable software? Reliable software could be defined like it will not produce more errors than specified, because then it's reliable. If you say it will crash every hour and it will do, reliable enough. If you cope with that, fine. But how to specify that, if it's good enough, mean time between failures, error probability, or errors per line of code, which are very funny metrics, by the way, it's up to you how to do that. And also it's up to you how to define an error, if it's critical, minor, or even a feature. And the difference between the fault and the failure, there are huge stacks of documents which describe the differences. As a matter of fact, you define it, what your reliable software will do. And if your definition is true, then it's good enough for your customer if he pays that for and if he takes the software as it is. After that, just have a look at the software development of the aerospace industry. Tom Stoppard, he is maybe known by you for the film Brazil, just stated that if Beethoven has been killed at the age of 22, it would have changed the history of music, but certainly also of avionics. And to understand what the challenges have been made and how long aerospace industry are dealing with that kind of software problems, I want to go a little bit back in the 1969. The Apollo, the whole world was looking at the Apollo landing on the moon, and one small piece was small in matter of history. This is the small piece. The computer over here has 32 kilobyte of code and 2 KB of RAM. It almost failed due to a procedural error because they just forgot to switch off the rendezvous radar with the main ship, and no one was there on the moon to ping back for the rendezvous radar. By the way, it was funny to see that this is the first stated occurrence of the 404 error I've ever seen, so maybe just a remark. 25 years later, a company called Boeing, maybe known by you, developed the 777, which was completely designed on computers. No line, no sketch was made by hand. And it's a full digital fly-by-wire flight controls. That means every command on the pilot will give is translated to an electronic thing. It's going through a computer and then to the actuators. And it's configurable. That means if you download a new software, it behaves completely different. Especially interesting because passenger planes are different than cargo planes. And if you want to use it for a cargo, then you have to have different avionics and that. And 4.5 million lines of new code have been written, and you can imagine that's quite a lot of code. Until now, no fatal incident has been reported. There is one on tanking on the airfield, but that's it. So you have to imagine it's really a bunch of software which had no failure, which caused a critical incident. And of course, currently the development hasn't stopped. If you have a look at the A380 and 787, where even more complicated scenarios are here, like multi-company, multi-site production, that kind of stuff. So, that's confidential information, I'm sorry. I also don't know that. But there was no bug which was found that caused an incident. And that's, I think, the most important thing. So, till now, it's 40 years of experience, and the aerospace industry developed a guideline called DO 178B. The B stands for the third approach. It was first 178, then 178A, and then B. B seems now to be quite good, and it is a guideline. It's a de facto development standard because it's accepted by the EASA and the FAA, which are the agencies, the government agency, which allow you to produce a plane and then transport passengers with it. So if you want to produce a plane, you have to ask them if they agree with you that you transport people with it and that you just enter the sky. It was developed by the RTCA and the Eurocare, which are not for-profit corporations. Please do not mistake that with non-profit organization. They might make profit, but they're not intended to do. It's more or less a corporation of engineers which give their experience and form guidelines and standards. And the only thing it does, it provides confidence and trust. Because if you have such a big plane and so many developers, they have to go on the same path, and they have to develop at the same type, so that they can trust each other, that they can trust the modules and the components which are developed. But it will not guarantee any safety. So if you develop according to standards and you develop something bad, then it will fail. But it will fail as specified. That's important. The DO 178B is not a standalone guideline. It's embedded in a huge of other standards. I have just took out the most important for them. It's the underlying document is the safety assessment, which just says that if you develop something, it has really to be follow guidelines and coding standards and this kind of stuff. Then you have the top level guideline, which is describing how you have to develop your system. System development is a little bit the high level view on development. It's not dealing with hardware or software. It just says, I have a plane, it shall fly, it shall not crash, and so on and so on. And from that system development, requirements, constraints, and software level will be transported or given to the software development process. Software level is something which I will explain later on. Requirements and constraints, I think that's quite clear. What is required has to be done, and what a constraint is that is a limitation. In the other way around, the software development will give to the system development the software architecture, how the fault containment will be done, and error sources. Error sources are very important because if they can't be handled, or if they're identified in software, then they can handle it maybe in hardware. On the hardware side, the similar thing goes on. From the system development, it will go with requirements, constraints, and the hardware level, and it will give back a hardware architecture and fault containment. Maybe it's interesting that there are no lines between software and hardware development. As a matter of fact, there are no connections. The only connection is over the system development. There is a pseudo connection, which is just a design trade-off. If I'm doing things smart enough in hardware, I don't have to do them in software, and vice versa. On guidance, there are some guidance documents also, an FAQ and a ground version. Because if you have something which is related to your plane, but located on the ground, it may have different requirements. So, now have a look at this piece in here, the DO-178B in itself. That's it, more or less. I don't think you can read that, maybe you can. It's a bunch of documents which are described by this guideline that they have to exist and how they interact with each other. So, and it's a very complex, it's not a very thick document. I think it has 130 pages, but you don't have to, if you don't know where to start from, you will be very confused. Most of the people start at chapter 2.2, which is failure conditions and the software level. The software level is that what I have also mentioned in an earlier thing. It's an interesting thing because it deals what a component can do for your system. Like, if it fails, is it a catastrophic failure? So the plane crashes, will come down, drops to pieces or whatever. Or is it only hazardous? That means it has a large negative impact. Or it has a physical distress and a higher workload on the crew of the plane. And by the way, if there are fatal injuries, that's also a case, then it's hazardous. The interesting thing is that the DO-178 and the developers has just recognized that a stressed crew and a heavy workload on a crew also endangers the safety of a plane, because if a pilot doesn't know where to look because of the many blinking lights, he will not see the mountain which is just in front of him. And then it goes to major, is it significant, to minor, where, yeah, you notice it, but yeah, maybe the coffee machine is broken, or it has no effect at all. That's an interesting category because there are components which don't have any effect if they fail. That's very important because if they are identified as that, they either can be replaced or just removed from the system because you don't need it, or they are isolated from the system, just to have that. So every piece of software will get an attribute of its capability on the safety of the plane. So if there, for example, if the primary flight control, it's certainly a level E, because if that fails, the plane drops out of the sky. But maybe the coffee machine is just level D because, yeah, it's inconvenient, but yeah, if it fails, then it fails. But if the coffee machine fails and the captain of the plane is just getting nervous, then it would be higher workload. So even the coffee machine could go to level B. It's a complicated process to really isolate the interconnections between components. And as Ariane 5 has